Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss full wave rectifiers as center tapped full wave rectifier and bridge full wave rectifier. Let's begin. In the previous video lecture, we have already discussed about half wave rectifier. The function of rectifier is to convert SC into DC. In this way, in case of half wave rectifier, one positive half cycle is converted as DC, but in case of full wave, both positive as well as negative half cycles are converted into DC. Full wave rectifier is an electronic device which conducts current during both the positive half cycles and negative half cycles of input AC voltage. AC is the combination of positive half cycle and negative half cycle. Therefore, as we convert AC into DC by using rectifier, in case of full wave rectifier, both positive as well as negative half cycles are converted into DC1. It utilizes both half cycles of input AC. There are two types of full wave rectifier. One is center tapped full wave rectifier, another one is bridge full wave rectifier. Let us discuss one by one. Center tapped full wave rectifier. Construction. The center tapped full wave rectifier consists two semiconductor diodes D1, D2. One diode supplies current to that of load resistance during positive half cycle of input AC, and another diode supplies current in the same direction to that of load during negative half cycles, load resistance RL. The input AC is applied across the primary coil of that transformer T. The end, you see the A end, that is the B end, the end A and the end B of the secondary coil S are connected to the P types of diode D1 and diode D2, and N types of the diodes D1 and diode D2 are joined to that of point X. One end of that of load resistance RL is connected to X and other end is center tapped at point C with the load resistance, that is the load resistance, its another end center tapped to that of secondary coil S of that of transformer T, and the DC output is obtained across the load resistance RL. One of the basic function of semiconductor diode is to rectify. Why semiconductor diode is used in case of rectification purpose? As we know, if a semiconductor diode is forward biased, at that of situation it conducts current. In its opposite way, if it is reverse biased, then it restrict the flow of current throughout that of junction. Therefore, we can easily use that semiconductor diode in case of rectification purpose. In this way, we use two semiconductor diodes D1 and D2. Let me explain the working. As input AC is applied, it is the combination of positive as well as negative half cycles. In graphically, let me show it. The voltage input graphical view, here we obtain voltage output. During the positive half cycle of input AC voltage, the end A of the secondary coil becomes positive and the end B becomes negative. Look here, A becomes positive, B becomes negative. So, positive, that is the P type semiconductor, and negative to that of N side semiconductor of D1. So, D1 is forward biased, and that way in D2 P type is connected to negative, N type is connected to positive. So, D2 is reverse biased. Hence, that D1 becomes forward biased and D2 becomes reverse biased. As we know, forward biased diode conducts current, whereas reverse biased diode restricts the flow of current throughout that of junction. Therefore, diode D1 conducts and diode D2 does not conduct. The current I1 is the amount of current flow I1 that flows through the diode D1 across that of load RL throughout that of upper half of the secondary coil S along clockwise direction. The flow of current here is the input voltage, and the flow of current direction current I1 upper half of that of secondary coil S in clockwise direction. Next point, during negative half cycle of input AC voltage, the end A of the secondary coil becomes negative and the end B becomes positive. A becomes negative, B becomes positive. So, D1 is now reverse biased and D2 is now forward biased. So, D1 does not conduct, but D2 conducts current. Hence, diode D1 becomes reverse biased and diode D2 becomes forward biased. Therefore, diode D1 does not conduct and diode D2 conducts, and the direction of flow of current, let I2 amount of current flow through that of diode D2 across that of load RL and lower half of S along anti-clockwise direction. The flow of current I2 amount of current flows lower half of that of coil S across RL in anti-clockwise direction, amount of current flow I2. It is observed that the current flows through RL is in the same direction for both half cycles of input AC voltage. In this way, DC output is obtained across that of load RL. Look here, from the upper half current flow along RL in this direction, again in lower half the current flow through RL in the same direction. Therefore, the output voltage we obtained of that of DC the time axis. Now, we obtain DC from AC by using center tapped full wave rectifier. This is the tapping, that center is tapped. The output we obtain across that load RL, V output. Two technical terms related to rectifiers, we have to discuss it. One is rectification efficiency and another one is peak inverse voltage. What will be the rectification efficiency in case of center tapped full wave rectifier? From the definition, rectification efficiency eta is equal to P DC, that is output power to the input power, output DC power to that of input AC power, power of AC. What is power of DC? P DC. Now, P DC is equal to I DC square RL. You have to calculate IDC. We know IDC is equal to 1 by 2 pi, that integration of I d theta. Theta varies from 0 to 2 pi in case of complete cycle, where I is the instantaneous current. It is given as 1 by 2 pi instantaneous current Im sin theta d theta, integration from 0 to 2 pi, whereas I is equal to Im sin theta. I is the instantaneous current. We change that limit 1 by 2 pi, that 0 to 2 pi, as 0 to pi and pi to 2 pi, Im sin theta d theta plus pi to 2 pi. Here the positive half cycle, in pi to 2 pi that is the negative half cycle, the theta will be negative, sin of minus theta d theta is equal to Im as constant on these two terms. So, Im outside, Im divided by 2 pi, first integral 0 to pi sin theta d theta, sin of minus theta minus sin theta minus pi to 2 pi sin theta d theta. is equal to Im by 2 pi integration of sin theta minus cos theta 0 to pi integration of sin theta as minus cos theta minus plus Im by 2 cos theta from the limit pi to 2 pi is equal to Im by 2 pi using upper limit and lower limit, that is 1 plus 1 plus Im by 2, again upper limit minus lower limit 1 plus 1 1 by 2 pi. Two to cancel out, Im by pi plus Im by pi, that is 2 Im by pi, 2 Im divided by pi. This is the value of IDC. Equation number 3. Now we put the value of IDC in that of equation number 2. Therefore, we obtain PDC is equal to square of IDC, it is 2 Im divided by pi whole square RL, or PDC is equal to 4 Im square RL divided by pi square. Equation number 4. We obtain PDC. Next, we have to obtain what be the value of power of AC, the input to AC power. Now, power of AC, I root mean square current RF plus RL, the reverse resistance forward resistance plus load resistance. Equation number 5, you have to obtain IRMS. Now we know that IRMS is equal to 1 by 2 pi integration over 0 to 2 pi I square d theta, its under root is equal to 1 by 2 pi integration from 0 to 2 pi I, that is the instantaneous current, Im square sin square theta d theta under root is equal to Im square to outside, Im square divided by 2 pi sin square theta in terms of cos 2 theta as 1 minus cos 2 theta divided by 2 integration over 0 to 2 pi d theta under root is equal to, solve that integral, half d theta as theta, Im square by 2 pi, that is theta by 2 minus sin 2 theta by 2 into 2 4 from 0 to 2 pi square root. Here Im square divided by 2 pi using upper limit and lower limit. In that of expression, it will be 2 pi by 2 under root I RMS. Now it is Im divided by root 2, the value of I root mean square. Equation number 6. We can put the value of I RMS in equation number 5. Therefore, power of AC is equal to Im square divided by 2 RF plus RL. Equation number 7, by putting the value of I RMS here. Therefore, the rectification efficiency eta, the value of PDC and PSC is put. Eta is equal to PDC by PSC. P DC divided by P of AC. P of DC 4 Im square RL divided by pi square whole divided by PSC Im square divided by 2 RF plus RL is equal to 4 Im square RL divided by pi square into 2 divided by Im square RF plus RL is equal to 8 divided by pi square RL divided by RF plus RL. The value of 8 by pi square as 0.812 RL divided by RF plus RL. Now RL is divided on both numerator as well as denominator. 0.812 divided by 1 plus RF by RL. That is the expression for rectification efficiency eta. Equation number 8. If RF is much lesser than that of RL, then the efficiency is maximum. Therefore, eta maximum, that value is equal to 0.812. In percentage, eta maximum is equal to 0.812 into 100%. Therefore, eta maximum as 81.2%. What exactly that signifies? Hence, a center tapped full wave rectifier, center tapped full wave rectifier can convert a maximum of how much? 81.2%. 81.2% of input AC power into output DC power. Output DC power. center tapped full wave rectifier can convert a maximum of 81.2% of input AC power into output DC power. Another technical term, peak inverse voltage. Peak inverse voltage is the maximum reverse voltage that a semiconductor diode can withstand without destroying the junction. In case of center tapped full wave rectifier, as we say, for positive half cycle D1 forward biased, D2 reverse biased, negative half cycle D2 forward biased and D1 reverse biased. As a result, the whole of the secondary voltage 2 times of that of maximum voltage across the non-conducting diode. Therefore, the peak inverse voltage for center tapped full wave rectifier is equal to 2 times of that maximum voltage. This is all about first type of full wave rectifier, that is center tapped full wave rectifier. Its construction, working, two technical aspects as rectification efficiency and peak inverse voltage. Another type, that one is bridge full wave rectifier. Its construction, it consists of 4 semiconductor diodes named as D1, D2, D3 and D4 in the form of a bridge. That diodes D1, D2, D3, D4 are connected in the 4 arms of that of bridge named as A, B, C, D. Input AC is supplied across the primary coil of the transformer T. The secondary coil S is connected between the two ends A and C of the bridge. The load resistance RL is connected between the other two ends B and D of that bridge. The DC output is obtained across the load RL. Let me explain the working of bridge full wave rectifier. As we apply AC, that is the combination of positive as well as negative half cycles. What happened in case of positive and negative half cycles? That will be the working of bridge full wave rectifier. During positive half cycles of input AC voltage, the end M of the secondary coil becomes positive and the end becomes negative. During positive half cycle, this is the M end, that will be the N end. M end becomes positive and N end becomes negative. So, diode D1 is forward biased and diode D3 also forward biased. But the diode D2 and D4 are reverse biased. Since M is positive, so it is connected to P type, that is forward biased. N is negative, it is connected to, that's N type. So D1, D3 are forward biased. Similarly, D4 and D2 are reverse biased. In forward biased situation, it conducts; reverse biased situation, it restricts the flow of current. Hence, diodes D1 and D3 conduct, but diodes D2 and D4 do not conduct, and the current flows through that of load RL along the direction A, B, RL, DC. The flow of current along the direction A, B through that of RL, DC, the flow of current. The direction of flow A, B, RL, DC. Okay. Next, during negative half cycles of input AC voltage, the M of the secondary coil becomes negative, but the N becomes positive. Therefore, the diodes D2 and D4 are forward, but the diodes D1 and D2 do not conduct, means they are reversed, and the current flow through that of RL along CB, RL, DA direction. Look here, during negative half cycle, M is negative, N end is positive, so it is connected to D2. So D2 is forward biased and D4 also forward biased, but D1 and D3 are reversed. So D2, D4 conducts current and D1, D3 restrict the flow of current. Now the direction of flow of current like this: C, B through RL and next through DA. There is the voltage, input voltage, and that of secondary coil. Next we obtain voltage output through RL. Final point, it is seen that the current flows through RL is in the same direction for both positive half and negative half cycles of input AC voltage. Therefore, DC output is obtained across the load resistance RL. Look here, during first positive half cycle, the flow of current AB, RL, DC along RL, it is from this direction. Negative half cycle, the flow of current CB, RL, DA, again it is in the same direction through RL. Now during positive half cycle as well as negative half cycle, the flow of current through that of load RL in the same direction. Therefore, you obtain output as a DC. It can be easily explained through that of graph. The voltage input, AC voltage, with the voltage output, or output you obtain DC. The time. Again, two important technical terms related to bridge full wave rectifier. One is rectification efficiency and another one is peak inverse voltage. So rectification efficiency, eta DC, power output to power input AC. Now power DC as I square DC RL. we know I dc as 1 by 2 pi integration over 0 to 2 pi I d theta is equal to 1 by 2 pi integration over 0 to 2 pi I instantaneous current Im sin theta d theta. Now the limit of integration we can change from 0 to pi Im sin theta d theta and pi to 2 pi, positive half cycle 0 to pi, negative half cycle pi to 2 pi, Im negative half cycle theta as sin of minus theta d theta is equal to Im as common, Im by 2 pi integral 0 to pi sin theta d theta. In that case sin of minus theta minus sin theta, so minus integration pi to 2 pi sin theta d theta is equal to Im by 2 pi sin theta integration minus cos theta limit 0 to pi minus plus as integration of sin theta minus cos theta Im by 2 pi cos theta limit pi to 2 pi using upper limit and lower limit, that will be Im by 2 pi 1 plus 1 plus Im by 2 pi 1 plus 1, 2 cancel out, Im by pi plus Im by pi, that is 2 Im divided by pi. This is the value of I dc, equation number 3. That value of I dc is put here. So we obtain P dc is equal to 2 Im by pi square RL, or P dc is equal to 4 Im square pi square RL. That is equation number 4. Next PSC. Now power SC, the input power I RMS square 2 RF plus RL. Here the forward resistance is the 2 times. Now you have to calculate the value of IRMS. Again with the equation number 5, I RMS is equal to 1 by 2 pi integration over 0 to 2 pi I square d theta, its under root is equal to 1 by 2 pi 0 to 2 pi Im square sin square theta d theta under root is equal to Im square, constant as outside, Im square divided by 2 pi integration over 0 to 2 pi sin square theta d theta under root equal to Im square divided by 2 pi cos square theta in terms of cos 2 theta integration over 0 to 2 pi 1 minus cos 2 theta divided by 2 d theta integration under root Im square divided by 2 pi, that integral as theta by 2 minus sin 2 theta divided by 2 into 2 4, that limit 0 to 2 pi its under root is equal to Im square divided by 2 pi into 2 pi divided by 2 under root, finally IRMS as Im divided by under root, at the value of IRMS. Now the value of IRMS is put in equation number 5. Therefore P of AC as Im divided by under root whole square 2 RF plus RL, or power of AC as Im square divided by 2 RF plus RL. This is equation number 7. Therefore that rectification efficiency, which is PDC divided by PAC, so value of PDC 4 Im square RL divided by pi square whole divided by PAC Im square 2 RF plus RL divided by 2 is equal to 8 by pi square RL divided by 2 RF plus RL is equal to that value as 0.812 RL divided by 2 RF plus RL. Now RL is divided both numerator as well as denominator. We obtain 0.812 divided by 1 plus 2 RF divided by RL, that is the efficiency eta. Now if RF is very less than RL, then the efficiency will be maximum, so eta max is equal to 0.812 in percentage, eta max as 0.812 into 100%. Therefore eta max as 81.2%. What it signifies? It signifies a bridge full wave rectifier can convert a maximum of 81.2% of input power into output DC power, that is input AC into output DC power. A bridge full wave rectifier can convert a maximum of that amount of input power AC into output DC power. Here peak inverse voltage of bridge full wave rectifier is equal to Vm, maximum of that reverse voltage. Since our positive half cycle D1 and D3 forward biased, similarly D2 and D4 reverse biased. Negative half cycle D2 and D4 forward biased, and D1 and D3 are reverse biased. Therefore the maximum voltage in that of reverse situation will be V of m. So, peak inverse voltage equal to V of m, that is bridge full wave rectifier, its construction, working, to technical terms, rectification efficiency and peak inverse voltage. So, here with the help of this video lecture we understand the concept of full wave rectifier, classification, center tapped full wave rectifier and bridge full wave rectifier. Center tapped full wave rectifier, bridge full wave rectifier, so with this useful and informative notes, let me wind up this session. Thank you.